Hello, everybody. I'm Fanyan Sun. I'm a PhD student at Stanford University. Yeah, today I'm going to talk about this topic that I've really been thinking a lot about, or, in one way or another throughout my entire research career. So yeah, let's dive into it. I actually started off doing a little bit of reinforcement learning, transitioned into graph machine learning, did an internship at Mila like years ago. And then I did an internship at NVIDIA 2 years ago, where I worked at the autonomous vehicle research group. And then I got really interested in 3D stuff. That actually led me to do another internship right now at NVIDIA, working on sort of compound AI systems for 3D scene generation. Yeah, but it's probably not hard to connect the dots between my experience and the work that I'm doing right now, because I worked a lot on graphs, and graphs are essentially a data structure that facilitates context selection. This is the outline. I'm gonna just take a stab at defining reasoning, and then introduce some of my works along the philosophy of this contextual intelligence idea. So I think reasoning is a very popular these days. It's been thrown around on Twitter, but there's so many types of reasonings, right? Common sense reasoning, mathematical reasoning. Like, can we come up with a domain agnostic way to define this? I think the answer to that is contextual intelligence. And let me explain. So there's two things in this definition, right? Contextual and intelligence. I'd like to borrow this figure from Francais Chollet, who is the creator of Keras, his paper on the measure of intelligence. The key idea is that intelligence should be defined as skill acquisition efficiency over skill performance. So if we formulate every problem in the world as, say, given some context, we are essentially, the problem is always like we want to extrapolate answer on some future unknown variables. And intelligence can be defined as the area of future unknown variables that one can cover or infer, right? So for example, a learning policy that is more sample efficient is more intelligent than its counterpart, even though it could perform worse than another algorithm that is just simply trained on more data, right? And I bring this framework of thinking up, because I think it's very useful to think about where and how to look when it comes to like improving upon the models we have today. I'm going to introduce sort of a graphical model perspective to foundation models. The first question is, what is in order to borrow that framework from Francais Cholet's paper, maybe the first question is, can we try to define a situational space in the context of language models or foundation models? And in this talk, I'm going to use them somewhat interchangeably. So we know that language models are trained to do next token prediction. So we can say, hey, maybe the situation space is just a sequence of tokens, right? And then you want to extrapolate to the next token. But thinking at this abstraction level is not very useful a lot of the times, right? So I like to define the situational space as it's essentially a random field of concept random variables. So you can imagine every point in this continuous space corresponds to a random variable, which corresponds to a semantic meaning. For example, if training data is like the capital of Francis pairs, then you can imagine this is just one observation of co-occurrences between these concept random variables within this random field, right? So during training, the model like sees tons of these like observations, and then after training, it essentially learns a set of these potential functions that cover every potential area. Every potential function covers an area within this random field. There are papers that point out that language models are primarily driven by co-occurrences of data. So an intuitive way to think about these potential functions is that they're just areas where language models have a lot of data to learn from and can robustly perform like one-shot inference within the area. And
A real quick clarification.
the reason I like to introduce this framework is because I think this is a very easy way to explain a lot of the things that we see in language models today. So for example, we'll start with a simple one, which is in context learning. Given a text like this, input France, output Paris, input America, output question mark. language models know the answer is Washington, D.C. Why? So effectively, language models sort of implicitly from the prompt activates relevant potential functions. So that's why language models wouldn't answer like North America in this case, because the potential function related to capital is sort of implicitly activated and selected. And this is just and it's a slightly more mathematical way of saying this is just that language model implicitly infers a latent concept, and then uses this latent concept to give the final outcome or the final output. So yeah, this sort of concept has been brought up in previous papers that I cited, but I think this also useful for us to think about the common failure modes in these foundation models. So this example is I guess, a very intuitive one to say, hey, like we know that language models are bad at sort of multi-hop reasoning. Yeah, because maybe there's not one potential function that covers both the observed region and the target region. And language models also just, there are a lot of, and you can think of this field as having a lot of gaps, right? Like, oh, language models aren't trained to do prime number factorization on given a huge number, right? Like that's like there are gaps in the random field that is a result of lack of data and or just like the formulation, right? The reason I introduced this is to think about the question of like how can we improve upon the reasoning ability of the models we have today. Let's take a step back and maybe do a little bit of a simple thought experiment, right? What are the hardest reasoning tasks that you as a human have done in your life? And I sat myself down and wrote down a couple things that I felt like are probably some of the hardest things I've done, at least in terms of like intellectually. So I've played a lot of Go games growing up. I feel like having to always like extrapolate 10 steps into the future, like that's like very mentally tolling. I've done some coding competitions, and sometimes I'm just like, yeah, if I'm just like a little better, I can solve these problems much faster. And then there's like higher level organization stuff where that, things I do in research where like I have a lot of things or like constraints that I'm considering at the same time. And I just feel like I'm running out of RAM. And in fact, when I'm preparing for this talk, when I was like, oh, I want to get these points across, and there's maybe some of these constraints that I want to work around, like this process is also not very, it's very sort of reasoning intensive. So how do I solve these problems, right? For Go games or for ACMs, I study relevant problems and identify motifs. So when I'm actually solving a problem, I'm saying, hey, this is a DP problem. And in my mind, I'm like retrieving relevant motifs or problems to sort of apply to this problem that I'm solving. A lot of the times when I feel like I'm running out of RAM, right, I have multiple monitors, and to show all the context of things that I want to consider simultaneously, and then I make decisions, and usually I use note-taking apps to enhance my productivity too, to organize my thoughts. I guess I had this a little bit of a realization that, hey, while I feel like, I could really use more RAM, right? Like this analogous to like language models could really use more context length. But I was able to get these things done, or at least reasonably well, because at every step I use these almost like productivity hacks to help me just focus on the relevant context that matters at this step of this decision. That led me to sort of hypothesizing that I think there's a big margin to be gained on top of the model performance we see today through engineering the context using compound AI systems. So I guess if we roughly divide sort of research up to like base model research and compound AI systems, frankly, I think base model research is also pretty interesting, but there are only a couple great places to do it at the moment. So given that I'm in academia, I say, okay, can we do this in compound AI systems, right? I'm not giving a definition of compound AI systems right now, but I can I'm broadly using that to refer to things like basically above base models. So the easiest variation of this is chain of thought, where instead of just having one prompt, you say like you have a chain of prompts to form the final prediction, right? And the framework that I introduced is also can be also easily used to explain chain of thought, right? So in this example, we're we're trying to answer, oh, like who's the what is the population of France's capital, for example, and then we can say, hey, we want to make direct prediction from the blue node to the red node in this like graphical model, and maybe they're linked together weakly by some potential functions implicitly learned, but it's not very the potential functions may be very weak, so you can't really make this one-step inference. Um, and but then we can say, hey, we can introduce an intermediate variable and marginalize over that intermediate variable to help with the prediction, right? Especially if we know that this intermediate variable will link like strong potential functions between the source region and the target region together, right? So this is this is why sort of chain of thought works, right? And people call it, I guess, scaffolded generation, where you introduce like a scaffold random variable. And so we've seen success mostly in the NLP domain for successful context engineering for building better compound AI systems. The question that I then ask is, oh, can we apply similar philosophies and principles to the vision and robotics domain, right? And because that's the domain that maybe I'm more interested in. This comes to the second part of my talk, which is sort of towards generating the 3D world. And you might ask me why do I care about this question? And the truthful answer is I just always think if we can generate a Google Map equivalent or a Google Earth equivalent that is purely generative and like interactable, that is just pretty darn cool. But in terms of application, I think, you know, these things, crafting the 3D world can be useful for designing 3D physical spaces. From a more research perspective, these 3D environments that we generate can be used to train reinforcement learning agents and robots. And in fact, the works that I'm going to briefly introduce are going to revolve around the use case of training robots within these environments that we generate. I'm going to introduce sort of first introduce two of my works sort of on compound AI systems in generating environments to train robots or reinforcement learning agents. The first work I'm going to introduce is Holodeck, language-guided generation of 3D embodied AI environments. This is a collaboration with UPenn and LNAI. The motivation is simple. LNAI previously introduced a work that procedurally generates environments to train object navigation robots. And they showed that by scaling this up, they can really sort of train better object navigation robots, essentially. But it's a procedural generation system at the end of the day. The diversity is limited, and the benefit of using these synthetic data tapers off after training on some amount of data. So the motivation is, can we use language model or VLM priors to guide this generation to actually generate more diverse environments, and we can also generate more targeted environments from language prompts. So the idea is simple, right? We say, hey, human-made indoor environments are decomposable. We can develop a pipeline in which each agent handles a particular aspect of a 3D scene and only takes to the context that we think it needs to perform the task. So most things are pretty straightforward. You know, you can think of this as like having a floor plan agent that's kind of like the architect. And then and I'm using agent as a glorified way of saying like it can be like, it's a decision-making process. It could be one prompt, could be sometimes multiple prompts, but they're just modules, right? And then the hardest part is actually the layout design module, which makes sense because it's the last part of this pipeline and needs to take the most context into consideration, right? Because when you as a interior decorator, you need to know sort of where the doors, windows are, and especially if you want to do language guided generation, then you have to also take the prompt into account. And there are a lot of, and especially if you want to place a lot of objects at the same time, then there's also it's also not that easy. And there's actually a lot of effort put into sort of using VLM to reprocess the assets and making the assets loadable in a physics engine, because we want to put these environments into a physics engine to train robots. But I'm going to not talk about that part, and I'm just going to focus on sort of layout design, which is the hardest part in this pipeline. The idea is language models are good at sampling semantics, so like scene graph-like things. And then mathematical solvers are really good at solving a very well-defined problem. So what about we marry the two and say we use language models to sample a scene graph, which essentially forms a constraint optimization problem. And then we use a solver. This could be a DFS solver, could be a mixed integer linear programming solver, to solve for the exact layout of the room or of all these assets in the scene. So some results, just basically language guided environment generation. These environments are interactable. You can put robots inside. We can generate diverse scene types from just language input. And we can put these scenes into VR and walk around in it. But yeah, for the experiments, I think, yeah, we compared with baselines on clip scores, in human evaluation, and the most important of all is probably the embodied AI environments, where we say, hey, we know a lot of the times we know where we want to deploy the robots. So we say, we're going to describe the environment that we want to train a robot in, and then generate those room types, fine-tune the navigation model on the rooms that we generate, and zero-shot test it on the novel environments. So we have 3D artists and engineers created 10 scenes, and then we trained a bunch of generated scenes and tested on these human crafted scenes on object navigation. We trained distributed PPO and showed that it was able to zero-shot transfer better just after training on the environments, the 3D environments that we generate. Okay, but limitations, like layout generation is still not great. There's still a long way to go, just because, language models probably don't have that prior. It's not trained on like coordinates and orientations of objects. And
Quick question: is the layout problem that you're solving a 2D problem or a 3D problem?
it's a 3D problem, but because we're solving for a layout problem within indoor environments, we do it in two stage, where we say first we solve for floor and wall objects, and then we solve for small objects that are placed on top of receptacles like tables.
I can see the constraints being natural for things like you don't want intersecting objects, right? Um, but a lot of the layout that you're doing has more to do maybe with like human convention and frequency. Like couches might face tables, might face end tables, and things like that aren't really hard constraints. So they're more of a learning conventions. So how do those two things figure in?
Yeah, no, that's a good question, and that's part of the limitation of this method. And in fact, we're improving upon it right now, with different methods. But yeah, I think in this previous version we say, because our goal is only to train object navigation robots. So we like say, if the language model says the sofa should be faced towards the table, then it's going to be faced to the table. It won't be like tilted 20 degrees counterclockwise. So yeah, that's just but I think there is an interesting question as to where we draw the line between like language models and like downstream tools or constraint solvers, right? Because maybe this at the time of this work, we think that this is like probably a very reasonable place to draw a line and say, okay, before this, we just use language model to sample semantics. And after that, we use constraint solvers. But yeah, we don't know if this is the best way to do it. Yeah. And actually, this actually kind of brings to the second bigger question, which is we hand engineered the context. Or, well, in this particular case, right, we say like, oh, there's a floor plan agent, there's a door and window agent, but in reality, these there there might be dependencies that we're not taking into consideration of. So, is there a better or perhaps more principled way to say select these contexts and not have to just always use human prior to decide on the decomposition of the problem? So that brings us to the second work we ask we ask the question, hey, can we use language models to self-refine and select relevant context for itself before it does the actual generation? So in this particular work, we aim to generate coded simulations of 2D environments and 3D tabletop robotics environments to train RL and robotics agents. So yeah, you can say that, see, the input is just sort of, they're basically descriptions of the target environments. From language, we generate code that describes the environment. We train robots within these environments and zero shot tested on the unseen testing environments. Perhaps we want to quickly formulate the problem a little. So since we care about RL and robotics use cases, we formulate the output as a POM-DP. And then we say, okay, we are essentially generating a code base that can represent a POM-DP. But if we do this naively, if the input prompt is something like this, it's going to fail. It's going to generate something that's inaccurate. So first thing we do is say, okay, we probably want to generate these things iteratively, component by component. And so it's kind of like modifying the code base iteratively to get to the final generation. Here's kind of like what it looks like in progress, where in this particular case, I'm iteratively trying to generate Flappy Bird. I'm saying, I'll generate this pipe generated in this bird, and it should be like have this logic when I click on it, blah, blah, blah. And very quickly, you would see that it's not scalable. First, because, say if the code base is now 2,200 lines long, the language models have to like take in the entire 200 lines of code into consideration and say, okay, I'm going to make modifications here. And so after sort of 10 prompts, this method quickly breaks down and like just sort of starts generating really buggy code. So how do I solve this problem? There are two problems in this. First, when the code base is long, like, it can potentially exceed context length. The second thing is we know from previous papers that irrelevant context can hurt language models' performance. So the idea is to select the minimal amount of context we need for the subproblem that we're tackling. Probably not going to go through the detail, but I want to point out sort of the key ideas and the philosophies behind this, which is the first step is, hey, we maybe first maintain a factorized representation of a code base, right? And in this particular case, these code bases represent POM-DPs or can be represented as POM-DPs. So this factorized representation essentially says that this code base, we have like a list of relevant state variables and a list of relevant functions. And every function, you can think of it as a hypergraph that pertains to a set of state variables. And then at each step of the generation, like for example, maybe I say, I want to add this particular logic to this environment that I'm generating. And then we would actually have LLMs select the relevant context, essentially select relevant parts of this code base that needs to be taken into consideration for this particular query. And then we form the prompts with only the relevant context selected by language models. And we combine this with a software design pattern commonly used in game design called model view controller. But essentially and then becomes this algorithm. Probably not going to dive into details, but going to talk about some experiments that we've done.
When we talk about LLM that selects that context, we're talking about GPT models or some other LLM? Just curious.
Yeah, in this work we just use language models to basically essentially self-select. So it's just another prompt.
No, I'm wondering like what language models?
I see. So in our experiments we did experiments with mostly GPT-4 and Llama 3.
Is there like difference between Llama 3 and GPT-4? Like if you remember like if there was like any difference in performance between those models?
Definitely. I think GPT-4 overall still performs better. I think one interesting thing that we observed is I think Llama 3 tends to, okay, this is empirical, but Llama 3 tends to seems to memorize a little bit more. So it tends to like output an entire code snippet and it's always the same code snippet, like for a particular game. So I think it exhibits the behavior of more memorization and less actual reasoning. But this is empirical, right? Like in the cases that we test or in the experiments that we've conducted, this is what we observe. But it doesn't like if you change maybe if you run the same problem multiple times, it's kind of like always the same program. Whereas with GPT-4, it actually generates slightly different programs every time.
Interesting. Okay, thanks.
Can you clarify on the POMDP kind of what the observations and actions are? I think the actions are focus actions, like focus on this context, and the observations are kind of whatever context you have currently. But can you kind of define?
Yeah, sorry. I should probably so the POMDPs here are the actual environments that we generate. In this say reinforcement learning game generation experiment, the action space is essentially the keyboard, and then we're generating say transition functions, right? So when the prompt might be when the user presses the key K, I want the bird to flap and goes up temporarily. And then we would generate the function that says if the key pressed, then we do this and that to the game state, for example.
So you are learning the policy that's going to be used for mapping keystrokes, history of keystrokes to which function is being selected. Am I interpreting that right?
Yeah, so we're generating code, right? This code essentially describes a game. It's a game that actually humans can play with too. And then we train a reinforcement learning within this game that we generate. So like with the game that we generate. In the first part of experiments, we basically first demonstrate that compared to baselines, we under the same amount of token usage, we can generate code that's more accurate to the prompt. And then we show after training on generated environments, without collecting any data or trajectory on the downstream like testing environment, we were able to show significant zero-shot transfer because the environments that we generate are at least more accurate in terms of logic, right? You can imagine if because RL is somewhat fragile, so if you implement the environment correctly, it can cause significant distributional shift. And with our method, we sort of have this method of like being more focused on generating different components and thus and have more focused context and was able to generate like more accurate code. And then we also apply this to generating robotics tasks or tabletop tasks. I think due to time, I'm not going to dive into the detail here, but you can basically think, using the same method, we can generate tabletop environments that we can use to train tabletop robots to do some manipulation tasks. So here are some tasks that are generated by our method, show that it performs better than other chain of thought methods, and particularly well, our method performs particularly well on generating assembly-related tasks. I think what are the main takeaways or the main points that I want to, I guess, want you to go away with. I think the first thing is, the main thing is like humans, we can enhance our models, quote unquote, productivity by engineering the context through better compound AI system design, right? So given whatever task you have at hand, you can write down the distribution that you aim to use language models to sample from. And then you ask the question, oh, if language models cannot do this in one shot, like, are there ways to factorize this probability distribution? To say, I either use other models or ways to essentially find regions or decompositions with more robust like potential functions, basically decompose the problem such that each subproblem can be robustly solved by the language model. Or you say maybe there are gaps that just is out of language models' inherent ability. So you use other tools to fill in the gap, like constraint solvers or mathematical solvers. But then you want to think about sort of how to, when you're designing a compound AI system, you want to think about what is the minimal context needed by each component in this compound AI system. And I think that's a really useful principle or philosophy when you're optimizing or designing a compound AI system. Currently, what I'm doing is essentially, I think one thing that's missing from these previous works is that there's no feedback loop. So right now I'm doing 3D scene generation and editing through code generation, where I can modify a 3D scene by language or image, generate diverse room types. The key point that I want to try to explore here is, hey, code is easily editable, interpretable, verifiable. Can we provide some sort of feedback loop to this compound AI system such that it can autonomously improve, or such that maybe I don't have to use a lot of prior to decide what the flow for the system should be. Maybe it's like I define the system in a very flexible way, but I just have some sort of reconstruction models or even diffuser models as feedback to optimize this scene generation system. Like on a higher level, what I'm excited about, I think, it's crazy how many models are at our disposal right now. You go to Replicate, Hugging Face, you can try out 100 models and get their APIs very, very soon. I imagine like very complicated but useful compound AI systems where you can think of, I was talking about language model as a graphical model, but there's an even higher level where maybe you can think of every node as a different model, and then we're all trying to solve a task or all come to an agreement together. And so this is kind of like you can think of, there's almost like another graphical model at the model layer, trying to do complicated tasks together or reach an agreement on a complicated decision. Yeah, and then there's using compound AI system to accelerate 3D workflow. That's something I'm also really interested in. And of course, along the line of works that I presented, if we can generate arbitrary environments to train agents to do a variety of different tasks, then we can potentially scale up the data we have for robot learning or reinforcement learning. And it's also a path towards training generalist agents, essentially. People call this direction generative simulation.